So, in today's class we will look at quadrilateral elements, and we will first look at derivation of shape functions for both rectangular elements and square elements with a different number of nodes, and then we look at similar to 1D elements, we look at isoparametric mapping concepts for quadrilateral element and also its limitation, and also we will discuss about numerical integration in 2-dimensional for 2-dimensional elements, and also derivation of element equations for 2-dimensional boundary value problem using quadrilateral element with different number of nodes. So, now higher order elements and elements with curved boundaries are effective when good approximate solutions are required with relatively few elements. So, that is the basic idea behind this quadrilateral elements. Theoretically, shape functions for any of these elements can be developed by starting from a polynomial of appropriate degree and then expressing the coefficients in the polynomial in terms of nodal parameters or the nodal values, similar to the way we did for 1-dimensional elements, both 2 node elements and 3 node elements, and also similar kind of approach we also adopted for deriving shape functions for 3 node triangular elements which are linear. This was the procedure used in the development of linear triangular element. This approach however becomes tedious and impractical for higher order elements, that is starting from a polynomial of appropriate degree and then trying to find the coefficients of this polynomial by substituting the nodal values or nodal parameters and corresponding nodal coordinates and solving these coefficients and substituting back these coefficients into the polynomial and grouping terms containing nodal parameters, common nodal parameters. So, that is how we derived shape functions for 1D elements and also linear triangular element, but that approach becomes tedious or impractical for higher order elements, that is, as the number of nodes for a particular element increases, we need to choose a polynomial having as many number of coefficients as the number of nodes for that particular elements. So, solving these coefficients and substituting back and grouping terms having the nodal parameters, common nodal parameters, becomes tedious for higher order elements. Fortunately, for second order problems, simple formulas exist that give shape functions directly for rectangular and triangular elements. So, we will be discussing some of these approaches, how to get these simple formulas in this class. So, this lecture presents shape function formulas for higher order rectangular and triangular elements, and these formulas together with isoparametric mapping concept play a fundamental role in development of development of elements for practical applications, because these higher order elements or element with curved boundaries are really required for solving some of the practical problems. The concept of isoparametric mapping was introduced earlier for 1-dimensional problem as a way to map actual element to simpler parent element. Basically, this is this was done for 1-dimensional elements to integrate some of the matrices and vectors that we get. shape functions, this is how we did. Shape functions were written for the parent element, integrations and differentiations were performed over parent element. So in this lecture the concept of isoparametric mapping will be extended to 2-dimensional problems. Using this concept, it is possible to develop quadrilateral elements and element with curved boundaries. So now let us start with derivation of shape functions for rectangular elements. For rectangular elements, the shape functions are based either on Lagrange interpolation formula or they are written directly from experience, and the elements which can be the shape functions of which can be obtained using Lagrange interpolation formula are classified as Lagrangian elements, and the other elements they are classified as serendipity elements. So now shape functions based on Lagrange interpolation formula the shape functions for rectangular and square elements are products of Lagrange interpolation shape functions in x and y directions as illustrated in the following examples. So basically we need to write Lagrange interpolation formula or Lagrange interpolation shape function in x direction and Lagrange interpolation shape function in the y direction, multiply these two, then we get the shape function for the particular rectangular or square element. This is how the procedure goes based on Lagrange interpolation formula. So now let us take a 4-node rectangular element. A 4-node rectangular element is shown in the figure. The coordinates of node 1 are denoted by x1 y1 and of node 2 are denoted by x2 y2, similarly node 3 node 4 etc. And also note that for this particular element that is shown in the figure, x coordinate of node 2 is same as x coordinate of node 3, similarly y coordinate of node 4 is same as y coordinate of node 3, similarly x coordinate of node 4 is same as x coordinate of node 1 and y coordinate of node 2 is same as y coordinate of node 1. So nodes can be denoted using the coordinates, or for simplicity nodal coordinates are identified by the node numbers. So now let us see how to derive shape functions for this particular element. If t is the field variable and t1, t2, t3, t4 etc. are the nodal variables, then the trial solution in terms of shape functions is expressed as first let us see only along line 1 2, along 1 2 you can see from the figure y is going to be constant, y is equal to y1, therefore shape functions must be function of x only. So now we are going to write shape functions along line 1 2. So that is denoted with t1, that is field variable variation along line 1 2 is denoted with t1 and it is going to be a function of x alone. n1 and 2 are going to be Lagrange interpolation functions, t1 t2 are the field variable values at node 1 and node 2. And from the knowledge of 1-dimensional elements we already know how to get N1 and N2. Using one dimensional Lagrange interpolation formula, we know N1 is equal to this, N2 is equal to the value or the quantity that is given there. So, we know how the field variable is varying along 1 2. Now, let us look at along side 4 3, and from the figure it can be easily noticed that y value along 4 3 line is equal to y 3 is equal to y 4, and field variable along 4 3 is denoted with T Roman letter 2, and that can be written in terms of shape functions of node 4 and node 3 in the manner that is shown there. That is, T2 is equal to N4 times T4 plus N3 times T3, which can be written in matrix and vector form in the manner that is shown. Again, from one dimensional Lagrange interpolation formula, T N4 and N3 can be written like this. So, we have seen how the field variable T is varying along side 1 2 and also along side 4 3. Now, let us look at take one of the sides which is along y direction. In y direction, so along 1 2 we know T1, and along 4 3 we know T2 from the previous equations. So, once we know the value of field variable along side 1 2 and 4 3 in the y direction, variation of T in the y direction, that is along side 1 4 or 2 3 can be written as T is equal to N1 T1 plus N4 T2, which can be written in matrix and vector form in the way that is shown there. And now, substituting T1 T2, and N1 N4 can be obtained by writing one dimensional Lagrange interpolation in y direction. So, that is how N1 and N4 are obtained. Expressions for side 1 2 and 4 3 can be written in matrix form, that is T1 T2 are written together in a matrix and vector form. So, substituting T1 T2 vector into the previous equation, we get this one. So, carrying out multiplications of N1 N4 vector with the matrix containing N1 N2 0 0 0 0 N3 N4, we get this, which can be compactly written like this. So, capital N1 is defined as small n1 as a function of x times small n1 as a function of y. Similarly, capital N2, which is shape function corresponding to node 2, is equal to small n1 as a function of y times small n2 as a function of x. Similarly, shape function of node 3, which is denoted with capital N3, it is equal to small n4 as a function of y times small n3 as a function of x. Similarly, shape function at node 4, which is denoted with capital n4 is equal to small n4 as a function of x times small n4 as a function of y. So, we can write what is capital N1, capital N2, capital N3 and substituting what is small n1 as a function of x, small n1 as a function of y, we get n1 like this, which is basically derived based on Lagrange interpolation formula in x direction multiplied by Lagrange interpolation formula in y direction at node 1. Similarly, shape function of node 2, shape function of node 3 and shape function of node 4. It can be easily observed that all of these shape functions, let us say n1 is going to be equal to 1 at x is equal to x1 and y is equal to y1 and it is going to be equal to 0 at all other locations. Similarly, n2 is going to be 1 at x is equal to x2, y is equal to y2 and it is going to be 0 at other nodal position. Similarly, n3 and n4 are going to be, n3 is going to be equal to 1 at node 3 and it is going to be equal to 0 at rest of the nodes. Similarly, n4 is going to be 1 at node 4 and it is going to be equal to 0 at rest of the nodes. So, the shape functions for rectangular elements are product of Lagrange interpolations in 2 coordinate directions. So, that is how we derived, and this is n1 and note that this is equal to 1 at node 1 and 0 at other nodes, and it is a linear function of x along 1 2 side 1 2 and linear function of y along side 1 4 and 0 along side 2 3 and 3 4, because node 1 is not part of side 2 3 and 3 4. So, it is going to be shape function of node 1 is going to be 0 along side 2 3 and 3 4. So, these properties not only shape function of node 1, but other shape functions of other nodes also satisfy these properties. So, shape function of a node is going to be 0 along sides to which it is not going to be a part, and shape function of a particular node is going to be equal to 1 at its own location and it is going to be equal to 0 at all other locations at all other nodal locations. So, other shape functions have similar behavior. Because of these characteristics, the ith shape function is considered associated with node I of the element. And the shape functions that we derived based on Lagrange interpolation formula, the same shape functions can also be derived from starting with a polynomial, and that polynomial is given here. So, starting with this polynomial we can derive same shape functions similar to the procedure that we adopted for triangular element. And if you see this polynomial, note that because of presence of term xy, the x and y derivatives of t are not constant, and if you recall, shape function or the shape functions, derivatives of shape functions of a linear triangular element are constant, and also derivatives of t field variable t are also constant for linear triangular element, because if you recall the polynomial that we used for deriving shape functions for linear triangular element do not contain this xy term, but now for this 4 node quadrilateral element, one way of deriving shape function is starting with a Lagrange interpolation formula, or the other way is by starting from a polynomial like this. And if you start with polynomial like this, you can see there is a presence of this xy term. Basically please note that this 1 x y xy, all these terms are coming from Pascal's triangle. So because of the presence of this xy term in this expression, the derivatives of t with respect to x and y are not constant, which was the case for triangular element, linear triangular element. So therefore this element generally gives better results than a triangular element. So we have seen how to derive shape functions for a 4 node rectangular element using Lagrange interpolation formula. So we can solve an example like this for shape functions. A 4 node rectangular element is shown, all the coordinates of all the nodes are also shown, xy coordinate system or xy axis are also indicated clearly in the figure, and these are the shape function expressions that we derived. So now if somebody is interested in writing shape functions for each of these nodes n1 to n4, simply we need to plug in the corresponding coordinate values into these expressions for n1, n2, n3 and n4. So x1 is equal to 0, y1 is equal to 0, x2 is equal to 3, y2 is equal to 0, x3 is equal to 3, y3 is equal to 2, x4 is equal to 0, y4 is equal to 2. Substituting these quantities into n1, n2, n3, n4 expressions, we can get the shape functions. Substituting the numerical values of nodal coordinates into the above shape function formulas, the explicit expressions for shape function for this rectangular element are as follows. So this is n1 after simplification, n2, n3 and n4. To visualize how the shape function varies as a function of x and y over the domain of that particular element, we can actually plot n1, n2, n3, n4 as a function of x and y, with x varying from 0 to 3 and y varying from 0 to 2. So similar kind of plots are shown here for n1 and n2, 3 dimensional plots of n1 and n2 are shown, and these plots can be obtained using any of the commercial software like MATLAB or Mathematica by just giving the expression for shape function and also the range over which plot is required, that is x going from 0 to 3, y going from 0 to 2. So this is how we can derive shape functions for 4 node rectangular element using Lagrange interpolation formula. So now let us take a 6 node rectangular element like this, and here also shape functions can be written in the manner or following the procedure that we adopted for 4 node rectangular element, writing shape function expressions along x direction and shape function expressions along y direction, multiplying both we get shape functions of each of the nodes. So the coordinates of node 1 are x1 y1 and those of node 2 are x2 y2, similarly other nodes. And you can see here in this 6 node rectangular element which is shown, node 2 and node 5 are interior to side 1 2 and side 6 4, and these nodes 2 and 5 are located arbitrarily on the side 1 3 and 6 4. So, now let us write the shape functions for all the nodes of this 6 node rectangular element following same reason. So, following same reasoning as for 4 node element, it is obvious that shape functions have quadratic variation in x direction and linear variation in y direction. If you see this the 6 node rectangular element along side 1 3 we have 3 nodes, along side 1 6 we have only 2 nodes. So, 2 nodes in y direction gives us linear variation in y direction, 3 nodes in x direction gives quadratic variation in x direction. So, following the procedure that we adopted for rectangular, a 4 node rectangular element, we can derive in a similar manner shape functions for all 6 nodes of this particular element. Here n1 is shown, n1 the shape function of node 1 is Lagrange interpolation formula in x direction, which is going to be quadratic because there are 3 nodes in x direction, times Lagrange interpolation in y direction, which is going to be linear because there are 2 nodes in y direction. The product of those two gives us shape function for node 1. Similarly, node 2, node 3, node 4, node 5 and node 6. And once we have all the shape functions, the trial solution can be written like this: T is equal to n1 times T1 plus n2 times T2 plus n3 times T3 plus n4 times T4 plus n5 times T5 plus n6 times T6, which can be written in a matrix and vector form the way that is shown. So, now let us take an example, numerical example with all the coordinate values given. So, here in the figure a 6 node rectangular element is shown, xy coordinates of all nodes are also can be easily obtained, xy coordinate of all the nodes can also be easily obtained using the information that is given in figure, that is x1 is equal to 0, y1 is equal to 0, x2 is equal to 2, y2 is equal to 0, x3 is equal to 3, y3 is equal to 0, and x4 is going to be 3 and y4 is going to be 2, x5 is going to be 2, y5 is going to be 2, x6 is going to be 0, y6 is going to be 2. So, with all this information we can, what we can do is we can plug in these coordinates of these nodes into the expressions that we have for shape functions n1 to n6, and we can get the shape function values of all the nodes, and also we can write the trial solution substituting the numerical values of nodal coordinates into the shape function formulas. Explicit expressions for shape functions for 6 node rectangular element are given here: n1, n2, n3, n4 and n5. and to visualize how the shape functions looks or how they vary along x and y directions, we can plot 3-dimensional plots of n1 and 2 are shown in figure below. And similarly shape functions of other nodes can be plotted. So, this is a 6 node rectangular element based on Lagrange interpolation formula. So, now let us look at another Lagrangian element which is 9 node rectangular element. A 9 node rectangular element is shown here, also x y axes are shown in the figure, and nodes 2, 4, 6, 8 can be located at any place on respective sides, and node 9 is located inside the element, and coordinates of node 1 is coordinates of node 1 are x1, y1, and similarly for the other nodes. And here you can see shape functions varies quadratically in x direction, both in x direction and y direction, because we have 3 nodes along x direction and 3 nodes along y direction. Here shape functions vary quadratically in both directions. So, writing Lagrange interpolation formula in x direction multiplied with Lagrange interpolation formula in y direction, we can write shape function expressions for all the 9 nodes n1 Lagrange interpolation x direction times Lagrange interpolation y direction, similarly n2 and the rest. And the properties that we have seen for 4 node quadrilateral element, the shape functions for this 9 node rectangular element also satisfies. So, that is if you see this node 1, this is the expression for shape function of node 1, and it can be easily verified that n1 is going to be equal to 0 at all other nodes except node 1, where it is equal to 1. And also it can be verified that n1 is going to be 0 along sides 3, 4, 5 and along sides 7, 6, 5. And along side 1, 2, 3 this expression is quadratic function in x, and along side 1, 8, 7 it is quadratic function of y. It is 0 at all other nodes except node 1, where it is equal to 1, 0 along edges 3, 4, 5 and 7, 6, 5, and along edge 1 or side 1, 2, 3 it is going to be quadratic function of x, and along side or edge 1, 8, 7 it is a quadratic function of y. And not only shape function of node 1, similar observations can be made for other shape functions. So, here when we are deriving shape function expressions for this 9 node Lagrangian element, basically we use Lagrange interpolation formula Instead of that, we can also start with a polynomial having 9 coefficients, and we can derive same shape functions. Same shape functions can also be derived from the following polynomial using procedure employed for linear triangular elements. So, this is the element for which we need to derive shape functions. There are 9 nodes, so we need to start with a polynomial having 9 coefficients like this, and we can adopt the procedure that we adopted for deriving shape functions for linear triangular element, and once we do that, we get same shape functions as we obtained using Lagrange interpolation formula. But only thing is, this procedure is going to be tedious, and also it is going to be cumbersome, since we need to solve for 9 coefficients and we need to group terms containing same nodal parameters or nodal values to get the shape function expressions. So, now we have the shape function expressions, explicit expressions based on Lagrange interpolation formula. For this 9 node element, we can write shape function for any element once we know the nodal coordinates. So, now let us take an example. Here a 9 node element is shown, x y axis are also shown, and also from the information that is given, we can easily figure out what are the x y coordinates of each of the nodes. So, once we have that information, we can plug this information into the explicit expressions for shape functions that we obtained using Lagrange interpolation formula to get the shape function expressions. Substituting the numerical values of nodal coordinates into the above shape function formulas, explicit expressions for n1, n2, n9 shape function for this rectangular element. Here, even though n1, n2, n9 are shown, we can easily write, or we can easily simplify the substituting the nodal coordinates into the previous explicit formulas, and we can get the shape function expressions for other nodes as well. And to visualize how these shape function n1 and n2 varies, we can even plot. So, here 3 dimensional plot of n1 and n2 are shown. For this particular 9 node element. So, we have seen a 4 node rectangular element, 6 node rectangular element, and 9 node rectangular element, and we have also seen how to derive shape functions of all these elements using Lagrange interpolation formula. So, these are the elements for which we can adopt Lagrange interpolation formula to derive the shape functions, but there are some other elements for which we need to adopt some other procedure. So, those set of elements are called serendipity elements. So, now let us look at those elements, serendipity shape functions for rectangular elements. Following shape functions for rectangular elements have been developed intuitively, hence the name serendipity, based on basic characteristics of shape functions, that is n1 is equal to 1 at node 1 and 0 at other nodes, or ni is equal to 1, ni is equal to 1 at node I and 0 at other nodes. So, instead of using Lagrange interpolation, or sometimes it is not possible to use Lagrange interpolation formula to derive shape functions for certain rectangular elements containing certain number of nodes. In that case, we need to derive shape functions intuitively without violating the condition that shape function of node I is equal to 1 at node I and equal to 0 at other nodes, using that basic characteristic of shape functions, and intuitively if we can derive the shape functions, and that is what serendipity element. Elements based on these shape functions are very popular. Their main advantage is that all the nodes are placed on element sides and thus there are no interior nodes. So now let us look at 8 node serendipity element, and it is a quadratic element. So it is called 8 node quadratic serendipity element, and xy axis are indicated in the figure, and also based on the information that is given in the figure we can easily figure out what are the x y coordinates of each of the nodes. And if you compare this element with the 9 node element that we have just seen, you can see you can notice that only the middle interior node which is 9th node is missing. So that is the only difference. So here before I show the expressions for this element, shape function expressions for this element, let us see if you want to derive shape function of node 1, and you can see from the figure node 1 is going to be 0 along edge 3 6, and node 1 should also be 0 along edge 7 6 5 in addition to edge 3 4 5. And if you can include the equation of line 3 4 5, equation of line of edge 3 4 5 and equation of line of edge 7 6 5 into this shape function expression of node 1. So then node 1 is going to be 0 along edge 3 4 5 and it is going to be 0 along edge 7 6 5. Similarly node 1 has to be 0 along or at node 2 and 8. So if we can come up, or if we can get the equation of line which passes through node 2 and 8, that can be easily derived based on the nodal coordinates of node 2 and node 8. We can easily write what is the equation of straight line that passes through nodes 2 and 8. If we can include that equation of that line also into the shape function of node 1, then we get the shape function including all the equations of sides 3 4 5 and 7 6 5 and also equation of line passing through node 2 and 8. If we include all this into the shape function expression for node 1 and normalize it, we are going to get finally the shape function expression, explicit expression for this 8 node quadratic serendipity element for node 1. Similarly we can derive for node 2, node 3, node 4, node 5, node 6, node 7 and node 8. So based on that we can easily write the shape functions for this element. Note that nodes are at the corners, and at the mid sides, and the origin of the coordinate system is at the element centroid for this element. So based on the procedure that I mentioned, when we are writing shape function for node 1, include equation of line passing through sides 3 4 5 and also include equation of line passing through 7 6 5 and equation of line passing through 2 and 8 and normalize it, then we are going to get shape function expression of node 1. Here it is written in terms of S and T, where S and T are defined. S is equal to 2x over A, T is equal to 2y over B. So this is how we can write shape function for rest of the nodes. So, adopting the explanation or the procedure that I mentioned, one can easily write shape functions for rest of the nodes, explicit expressions for all the nodes, all the 8 nodes are given here, and it can be easily verified that each of these nodes is equal to 1 at its own position and it is equal to 0 at the other nodal locations. It can be easily verified that the shape functions have the desired properties, that is n1 sorry n I is equal to 1 at node I and n I is equal to 0 at other nodes. So, here we used some kind of reasoning, or we have developed whatever expressions that I have shown, we have developed for this element intuitively by making sure that it is a shape function at a particular node is equal to 0 at other nodal location. We have derived the element, we have derived the nodal shape functions, explicit expressions of nodal shape functions intuitively. Instead of that, we can also start with a polynomial, taking a polynomial having 8 number of coefficients. These shape functions can be derived from the following polynomial using method that we adopted for linear triangular elements. So, since there are 8 nodes, we need to start with a polynomial having 8 coefficients. So, this is the polynomial with which you can start and adopt the procedure that we did for linear triangular elements, and finally we can get same shape functions as we have seen, and the 3-dimensional surface plots of these shape functions are similar to those of biquadratic Lagrangian shape functions. So, now we have derived shape functions for 4 node element, 6 node element, 9 node element and 8 node element. So, we can write shape functions for all elements with nodes having nodes from 4 to 9. So, here we will write a general set of shape functions to define shape functions for any rectangular elements with nodes ranging from 4 to 9. The complete set of shape functions will be given in the in a table, and but the ordering of nodes or the ordering of element node numbers is very important. So, the expressions that I am going to show you are valid only for this node numbering. With this particular node numbering scheme, shape functions for higher order elements are constructed by adding terms into shape function for lower order elements. Here there is a typing mistake in the title, it should be shape functions for 4 to 9 node rectangular element. So, complete set of shape functions for any element with nodes from 4 to 9 are given in table below, and the following notation is used for the expressions that are given in the table. S is defined like the way it is done earlier, S is equal to 2x over A, T is equal to 2y over B, and F1, F2, F3, F4, F5, F6, F7, F8 and F9 are defined like this. The shape functions expressions for all nodes of an element having 4 to 9 nodes is expressed in terms of these f's. So, this definition of f1 to f9 is very important to read the table. So, the table expressions for shape functions of all nodes for 4 to 9 node rectangular elements are given. 4 node element, 5 node element, 6 node, 7 node, 8 node and 9 node element. And please note that elements with number of nodes between 4 and 8 are known as transition elements. These elements are useful when a transition from quadratic to linear element is desired. So, using this table we can derive shape functions for any noded element starting from 4 node to 9 node element, and we will continue in the next class.